Yeah, as I said, the next speaker is Jessica Haber from Irvine. Please take it away, Jessica.
Cool. Sorry, I'm wrestling a little bit with the gallery view just to make sure I can see everyone also. Okay, cool. Well, hi everyone. And first off, thanks so much to the organizers for putting on this wonderful workshop and also for inviting me to speak. I'm very sorry that I couldn't make it in person, but I'm still really glad that I can participate virtually. So thank you, Zoom. And I'm really excited also to talk to you about this work, which considers an alternate cosmological history in which there was a period of electroweak force confinement that was happening at the same time that dark matter was freezing out in the early universe. And this project was a lot of fun, and there was also, in addition to a lot of fun physics, there was also some fun kind of coding in Python as well. That was a large component of this project. And so if that's something you're interested in, I also have the GitHub links up here as well. Okay, so as we're probably all familiar with, particle interactions dominated in the early universe, and the nature of these interactions would have had profound downstream effects for how our universe looks today. So in principle, understanding these particle interactions at high energies in the lab can help us to better understand this early universe time period and the effect that it would have had on our universe's evolution. And in fact, extrapolating our knowledge of particle interactions from the standard model is what leads to the standard cosmological history. However, extrapolating the standard model back in time in this fashion is fundamentally an assumption, and the real cosmological history during this early universe time period might differ in key ways. And in principle, we would need more direct probes of this time period to say definitively what exactly happened. Now, whether the standard cosmological history is the true cosmological history would be a philosophical matter, except that we know that the standard model is incomplete and cannot explain certain cosmological features in our universe. And two very key examples of this are why our universe is made of matter and not antimatter. There's no satisfactory explanation for this asymmetry in the standard model. And also the abundance of dark matter in our universe. There isn't a particle in the standard model that can currently fill this role. And at the same time that we have these kind of issues with the standard model, we've also only probed the standard cosmological history with direct measurements back to BBN, occurring at temperatures of about 1 MeV. And so this leaves plenty of room for alternate cosmological histories during this very early universe time period to help us provide explanations for these currently unexplained features. And I want to take a moment just briefly to more broadly motivate the why for exploring a very wide range of alternate cosmological histories. And the most obvious motivation is that it might lead to some profitable physics results. And I'll be giving an example of this related to dark matter in this talk. But I also think that considering the full range of possible alternatives is just an important scientific endeavor. Since experiments have not ruled out these alternatives yet, it's our responsibility as scientists to kind of chart the full range of possibilities. And in doing so, in charting these possibilities, I think this will inevitably help us come up with probes to figure out what the actual cosmological history really looked like. So I think there's a lot of reasons why studying these kinds of scenarios are important. Okay, so now the question becomes, how do you modify the cosmological history? And we're actually used to modifying cosmological histories in certain ways. So for example, it's pretty common to add new BSM particle species and explore their early universe cosmological effects. But the modifications during this time period can also be much weirder. And so for example, you can modify the strengths of forces in the early universe. And the general idea here is that there were features in the early universe that could have caused the strengths of the forces to evolve and eventually settle into what we see today. And there's been many works that have explored the cosmological effects of such modifications, and I give a couple of relevant examples here. But in this talk, I'm going to focus on this kind of scenario where the electroweak force is varying in the early universe. And I'll be talking about the effects that can have on kind of a WIMP-like dark matter freeze-out scenario. And this work is largely based on a very interesting paper which considers a period of electroweak force confinement early in the universe. And so this work essentially throws a dark matter candidate into that mix. Okay, so in a WIMP freeze-out scenario, there are really two main dials that you can tune in order to get the correct relic abundance of dark matter that we see today. There's the mass of your WIMP particle and also the strength of its interactions. And a simple and classic WIMP scenario assumes that dark matter is a weakly charged particle. And because it is weakly charged, the coupling strength is fixed. And so having fixed one of our knobs, this means that in principle, there is a unique mass for our dark matter candidate that will give us the correct dark matter relic abundance. However, this scenario is strongly constrained by experiments. But what's been going on in the background is we've been implicitly assuming that we had a standard cosmological history. And so if the cosmological instead, if we have an alternate cosmological history, for example, one where the electroweak force coupling was different than its present day value, during dark matter freeze-out, you can immediately see how this would help us restore some freedom into this mass dial. And this is the scenario that we're exploring, we explored in this work. So to briefly sketch what this calculation looks like at a high level, I'll first note where we are on the timeline. And so WIMP freeze-out typically occurs in this range, which is far out of the reach of current direct experimental constraints. And now to get our varying force strength, the mechanism that we use is to link the force coupling to the vacuum expectation value of a scalar field phi that is undergoing a phase transition in the early universe. And now when this VEV is very small, near zero, our electroweak force is at its normal strength. But when it gets large, this is actually going to cause the electroweak force to become much stronger and actually trigger a period of electroweak force confinement, which is very analogous to what happens in QCD. And now in this work, we assume that this period of electroweak force confinement is occurring at the same time that our WIMP particle is freezing out. And during this time, the WIMP dark matter, along with standard model quarks and leptons, are going to be confined into pion-like objects. And it's these dark matter pions that are going to be undergoing freeze out. And so these dark matter pions interact and can produce pions that contain only standard model particle content. And when these processes can no longer occur, the dark pions have frozen out. Now, eventually, our phi VEV is going to trend towards zero, which is going to end this period of electroweak force confinement and kind of return us to the standard timeline. So at this point, the pions are going to deconfine and give us a relic abundance of our WIMP dark matter that we would see today. Okay, so our dark matter is a pair of vector-like weakly charged Weil fermions with these quantum numbers and following this Lagrangian. And during electroweak confinement, these chi's are going to be trapped along with standard model quarks and leptons into bound states. And these are analogous to the mesons and baryons of QCD. But we only consider the lightest of these states, which are mesons named in analogy with their QCD counterparts. So pions and the eta prime. And so if we follow some lessons from chiral perturbation theory, we can collect these into a field sigma, which allows us to kind of better parse what's going on in this confinement. So let's look at the confinement in a little bit more detail. So this electroweak confinement is going to spontaneously break flavor symmetry from SU2NF to SP2NF. And this follows intuition from chiral symmetry breaking in QCD, but has also been confirmed in lattice simulations. And we can encode this explicitly by placing a condition on sigma's VEV, which you see here. So if we, for a moment, neglect other standard model gauge interactions and Yukawa couplings, this breaking, spontaneous symmetry breaking would produce a number of massless Goldstone bosons, where the number of those corresponds to the number of broken generators. And we also get one massive pseudo Goldstone boson in analogy with the eta prime in QCD. And under this setup, we consider two cases. There's a toy model where we have only one generation of standard model quarks and leptons, and also the more realistic 3-generation case. And just to contrast these, in the 1-generation case, we have SU6 breaking to SP6, and so we're going to get 15 mesons, where in the 3-generation case, we have SU14 breaking to SP14, and now we get 91 mesons. And so the calculation proceeds similarly in both cases, but the 1-generation case is much more tractable. It's easier to keep track of a smaller number of pions. And so I'll be focusing on this one to better gain some intuition about what's going on. Okay, so in the confined phase, the sigma field follows this IR Lagrangian, and you can also see the explicit form of sigma over on the right, where these X's are the generators of the broken symmetry. But in addition to this Lagrangian, there's also a term which corrects for the fact that the flavor symmetry is also being explicitly broken by the other standard model gauge symmetries. And so this is going to result in giving mass corrections to some of these would-be Goldstone bosons. And in addition to this, confinement is also going to break these symmetries into their subgroup, which is going to further eat more massless Goldstone bosons. Okay, so it's interesting to take a look at the spectrum of meson properties. And so on the right, I show how the masses relate to each other for the two benchmark parameter space points that we considered. And then on the left is a breakdown of the gauge charges of these mesons. And some things to note here is that one, the eta prime shown in teal is much heavier than all of the other mesons, and thus is going to be Boltzmann suppressed. And so we ignore it in the following calculation. And we can also see that the pions, which contain dark matter shown in orange, are quite a bit heavier than their standard model counterparts shown in purple. And so we can see that we can also see that there are small differences between the orange masses, but that the first benchmark point, BP1, lifts this degeneracy somewhat. But because they're also close together, we need to consider the possibility of co-annihilation in the calculation. So now that we have the spectrum of pions that we're dealing with, let's actually get into calculating the interactions. And so since we're calculating the freezeout of dark matter pions, we are interested in the reactions which deplete the dark matter density. So reactions that take pions containing dark matter to pions containing only standard model content. And so from this IR Lagrangian, we can extract the 2-to-2 reactions into the following form, where this TR1 and TR2 are functions of traces of the broken generators. I'll just note that for the benchmarks that we chose, we can safely neglect annihilation into gauge bosons. Okay, so with these interactions, we are able to calculate the effective cross-section, taking into account the possibility of co-annihilation. We're assuming that the incoming pions are non-relativistic and that they have S-wave scattering. And because of the many different possible combinations of these A, B, C, Ds, we decided to perform this calculation numerically in Python to make it tractable. And then finally, so we use this effective cross-section to solve the Boltzmann equation for this final co-moving number density of dark pions. Okay, so taking a step back to look at the bigger picture again, freezeout is happening while our dark matter candidate is in pion form. It's going to be the lightest pion which contains dark matter that's going to survive this freezeout process. And so we're calculating its final abundance numerically. However, this pion is not going to live until today. Eventually, the scalar VEV is going to trend back towards 0, which is going to end our electroweak confinement and return us to the standard timeline. And when the electroweak forced confinement ends, or when this electroweak confined phase ends, the pions are going to deconfine. And I'll note that the entropy dump from this deconfinement we assume is negligible, which would prevent further freeze out of these dark matter, the dark matter candidate chi. And then one final adjustment to note quickly is that we need to convert the relic dark pion abundance into the relic dark matter abundance, which is what we would actually observe today. So with these adjustments, we were able to do a parameter scan and fit the abundance of these chi's to the experimental results. And so now for the results. So here we show the 1 and 2 sigma agreement for the toy 1 generation model on the left, and also the full 3 generation model on the right. And the z-axis, so the color axis is the effective velocity averaged cross section of the dark matter pion during freeze out. And for both of these cases, we can see that the mass range is quite similar. And in the 3 generation case, we can also see that the viable range of the effective pion decay constant shifts up a little bit. Okay, so we went through all of this model, but now the question is it ruled out? And kind of the most immediate concerning experimental constraint would be direct detection, because as a reminder, our dark matter candidate are weakly charged doublets with hypercharge and full strength Z boson interactions. And so this would really spell trouble for being ruled out by direct detection experiments. However, we can pretty easily sidestep these by introducing a small Majorana mass that is present today for these particles. And this can be induced, for example, through a dimension 5 interaction with the Higgs. And also, provided that these mass scales M1 and M2 are large, this effect wouldn't have played a role during freeze out. And so the calculation that we performed would still be valid. Okay, and then how does it fare with other experimental constraints? So for the LHC, this would have an analogous signature to charginos, which are not currently constrained for masses above 420 GeV. And also, unfortunately, a order 10 TeV particle is also likely going to be out of reach of future colliders. On the indirect detection side, this provides probably the most promising avenue for detecting this kind of dark matter model and might be in the reach of future gamma ray observatories. So I'd like to take a moment to contrast what I just described with the case of a WIMP-like particle in this mass range in a standard cosmological history. And so while a standard cosmological, or while a WIMP, which underwent freezeout in a standard cosmology, also in this mass range, also wouldn't be experimentally ruled out, it crucially wouldn't give us the correct relic abundance that we observe today. And so this alternate cosmological history is what allows us to have this flexibility. So to say it another way, this alternate cosmological history allows us to maintain the correct dark matter relic abundance while increasing the possible mass range of dark matter, which is effectively restoring some freedom to WIMP models. Considering alternate cosmological histories is both important and can also be advantageous. And with a modification to the cosmological history, we were able to show how this can help restore some freedom to WIMP dark matter models. And this is not currently ruled out by experiments. So thank you so much for listening, and I'm happy to answer any questions now.
Questions for Jessica?
Yes. So thanks for the great talk. I'm just curious if you guys have thought about possible UV complete theories that can actually give rise to such a dynamics in the IR.
Yeah, no, that's a great question. So yeah, so in this work we stayed, we tried, sorry, maybe I could go back a few slides. Yeah, so in this work, we tried to stay very agnostic to this phi and what its phase transition looks like, and the UV dynamics that would have caused this. But I think it would be very interesting to explore those as well. But we haven't thought about that too much at this point. But the process here is quite general, so you can kind of patch in whatever UV theory would lead to this sort of case.
Okay, so I guess one of the, I don't know. So in other words, for example, fermions or other charged state under this case group will like have effective coupling, which is inversely proportional to the VAB of scalar field, which at least didn't look very, feasible, but maybe there's a UV complete theory. In any case, thanks for the answer.
Oh yeah. Yeah, that sounds very interesting. I'd be very interested in chatting more with you about that.
So while we're at this slide, let me just ask a follow-up question on this. So you look at an interval of time in the early universe where G effective is very large, but from what you're writing down, you need some tuning to get that large G effective. That means, well, VEV and couplings, everything is running and changing with temperature. How long can you preserve this big tuning to get a large G effective?
Yeah, so I think it's pretty. I think it's pretty.
Sorry, let me ask it. Sorry, yeah. To make it just more sharper. For what range of temperature can we get this behavior? Have you thought about? Is it 1 order of magnitude, 2 order of magnitude?
Yeah, no. Yeah, that's a great question. I would say that I think it's fairly robust, although I don't have a specific temperature range. We didn't think about that in too much detail. We're just assuming that we're happening before the kind of standard electroweak phase transition point. But yeah, so there's a lot of different mechanisms that you could think of that would give you this evolving VEV. And so really the only pieces that are required here is that it starts at some large-ish, but not too large value, and then trends towards 0 with time. But the exact duration of that, no, we didn't really look into that.
Yeah, cool, thank you.